Hello viewers, I discuss today general Bessel's inequality. Actually it is known as Bessel's inequality, but in earlier video I discussed Bessel's inequality for finite cases, finite orthonormal set, but here I discuss general Bessel's inequality in functional analysis. At first we are going to the statement. If EI is an orthonormal set in a Hilbert space H, then summation x dot ei mod whole square less than equals to norm of x square for every vector space in Hilbert space H. Now let's look how to prove this result. For the part of proof, let here we consider S for the orthonormal set EI, and EI is such that x dot EI that not equals to 0. So here we consider the non-empty cases. Then either this S is a empty set, that criteria is not satisfied, or it is countable. These two cases arises, and if S is empty, that means here we consider our construction of the set S, and if this is empty set, then this criteria is not satisfied. That's why this cases is equals to 0, and this is empty. If S it is empty set, then x dot ei that will be 0, and this case hold for all I. That means I runs from 1 to up to infinity, whatever may be, we consider 1 to up to infinity, and in these cases we define that is a summation mod of x dot ei, that's whole square, to be the number it is number 0, and we have this result. That means it is a number, and we have 0 is less than norm of x square, and that is norm of x square is greater than equals to 0. That is a non-negative property, and thus if S is empty, and then we have summation mod of x dot ei whole square that will be less than equals to norm of x square, and this is a trivial cases. It is a trivial cases. Now suppose that S is non-empty, then how to prove this result? Then either this S is finite or infinite. These two cases happen, and at first we are taking is finite. If S is finite, then this is equal to E1, E2 up to En, these cases. And for some I belongs to positive integer, that is a Z plus, if we are taking in this notation. And in these cases, we define in this case we define summation mod of x dot ei whole square, and that will be summation I runs from 1 to up to n, that's a finite case, x dot ei whole square for, and certainly which is less than equals to norm of x square by Bessel's inequality for finite case, and which we already proved in my earlier video. I am already discussed, I have this, how this result proof for Bessel's inequality for the finite cases. So we are nothing to prove here. For the details, discuss this video how to prove this result of the finite cases. Now we are taking, suppose, is finally we are taking infinite cases. Now for infinite cases, and it is countably infinite for our arranging definite order, S is equal to E1, E2 up to En dot 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 up to infinite level. We are taking, consider in the vectors, let us the vector in S be in infinite order, and let us define mod of x dot ei whole square is equal to summation n runs from 1 to up to infinity mod of x dot en whole square. This is our infinite cases we are taking, but this result is these sums will be well defined only. This sum will be well defined only if we can show the series summation n runs from 1 to up to infinity mod of x dot en whole square is convergent. This is the main criteria we are going to prove, and this is a convergent result, and this arrangement but any arrangement in the finite cases for the vectors in the set S we have by Bessel's inequality. It is a finite cases for n I transform here because here if we are taking here the suffix for the finite cases we are taking sum of I equals to 1 to up to n norm mod of x dot ei whole square less than equals to norm of x square, taking it equation number 1. Then from 1 the series from 1 the series summation n equals to 1 to up to infinity mod of x dot en whole square is convergent. And since all of the terms of the series are positive, since all of the terms of the series is positive, and therefore we can see that's absolutely convergent. And this by we define by the justification we define summation mod of x dot ei whole square is equal to summation n runs from 1 to up to infinity mod of x dot en whole square. From 1 we see less than equals to norm of x square. So in this way we prove and we end our discussion today. If you like this video, like it, share it, and don't forget to subscribe the channel. Thanks for watching.